Thank you for the introduction, and good morning. Thanks for attending the first session of the last day. And I'd like to thank the organizers for inviting me. It's my third time at CQIQC, and like the previous two times, it's been a really great conference. So it's a pleasure to be able to talk about this work. So in this work, we measured the modal structure of quantum light using this technique of intensity interferometry, which I'd like to tell you about. Okay, woke up. So by modal structure of light, I'm really just talking about the shape that a beam of light has in its different degrees of freedom. So of course, these are the polarization, space, momentum, and time and frequency degrees of freedom. And in general, the beam can have both an amplitude and a phase in all three of these degrees of freedom. And this gives quite a large space that physicists and engineers have been using to encode information both in classical light and in quantum light. So this is just an example of some of the bases that have been used. So because you have this big space, it's great for encoding information, but it also makes the characterization generally a hard problem. So in particular, when you have these correlations between the different degrees of freedom. So you can have these vector beams, just shown here on the left, where there's a correlation between the spatial mode and the polarization, which is denoted by these red vectors. So, besides the obvious reasons why you'd want to measure the mode structure of light, like imaging, I'd like to focus a little bit on the third point here, given the context of this conference. So, as we're scaling up photonic quantum technologies, it's very important to develop sensitive ways to characterize the modal structure of these quantum light sources, because we're inevitably going to have to interfere independent sources. And we saw a nice talk by Chaoyang Liu where he showed this kind of tour de force experiment. They interfered 20 different sources, I think it was 20. And Xanadu is building kind of similar experiments on chip where they're trying to also interfere lots of different quantum sources of light. And so the quality of the entangled state that you prepare in these photonic platforms depends on how well the photons are interfering. And so you can kind of understand that in this simple picture with the simplest interference, well, maybe one of the simplest interference experiments you can do, this entanglement swapping between Alice and Bob. So say Alice and Bob send one of their photons from their pair sources onto a beam splitter to do the Bell state measurement. And in optics, the Bell state measurement relies on Hongo-Mandel interference. Okay, and the quality of that interference will dictate the quality of the entanglement swapping. Of course, this depends on how indistinguishable the photons are, but it also depends on the modal purity of the photons. So I can have two photons which are in modal mixtures, but are indistinguishable from one another, and they won't interfere well. So you really have to be careful when you're characterizing your light. So the two big challenges when it comes to determining this modal structure is that we're dealing with optical frequencies, and our detectors, of course, are limited to electronic timescales. So they measure some sort of time average response of the field. So we're inherently insensitive to this phase. And so we have to do some sort of interferometric measurement to get that information. And this is true in classical optics, of course, as well as quantum. The second thing is that now there can be these non-classical correlations between the photons. And so this arises very naturally, for instance, in these spontaneous parametric down-conversion sources where you're pumping crystals and you produce from one pump photon two lower energy photons, typically called signal and idler. Because of the energy conservation of this process, there can be strong correlations between the frequencies of the down-converted photons. And so now these photons actually live in a mode which can't be described for each individual photon. They're entangled. So you have to do some sort of joint measurement to describe their mode. So this is just to say that the techniques that we have for classical light aren't always going to be applicable in the quantum domain, but of course we can try to adapt them to suit our needs, which is kind of the point of the talk today. So I'll tell you about this technique of intensity interferometry, and I'll demonstrate two experiments that we did. The first was to measure the spectral mode, the joint spectral mode of photon pairs, and this was work that I did with colleagues at Imperial College London in the group of Ian Walmsley. So then I continued this work at the Canadian National Research Council in Ottawa in the group of Ben Sussman's, where we're essentially doing the same measurement now in the spatial domain. Okay, so let me be a little bit more precise about what I mean by the mode structure of light. So if we take the example of a single photon, a multi-mode single photon can be written in this way. So there's the creation operator acting on mode n, and the shape of mode n is specified by this complex valued function f sub n. Okay, so this complex valued function will satisfy Maxwell's equation. It doesn't tell you anything about the statistics of the light field. It just tells you about its mode structure. Okay, so because I like to understand by examples, you can think about spectral modes. When you first do quantum optics in textbooks, you always or often deal with these monochromatic photons. You have a creation operator acting on a particular frequency mode, omega. So the spectrum of that photon will be this Dirac delta function at omega. This is not a good description of what we make in the lab. So we typically have pulses of light, and the photon lives in this pulse mode. So the way that you'd write that is with this complex valued function psi. And you can interpret that function the exact same way that you interpret a classical pulse envelope. So the absolute value of that tells you about the spectrum of the light, of the single photon. And the argument tells you about spectral phase. So spectral phase, for those of you who aren't familiar, tells you something about how the time of the light is correlated to its frequency. So if you have, for instance, a quadratic spectral phase, we say that the light's chirped, has a linear chirp. So in this example, higher frequencies arrive before lower frequencies. Okay, and you can extend this to mixed states by having an object that looks like a density operator. So that was for a single particle. We want to extend it to pairs of particles. And so the sorts of things I'm thinking about are these nonlinear processes like Fourier-wave mixing and parametric downconversion, which produce like these signal annihilator photons. And these live in this joint spectral mode now, which, as I said earlier, generally can't be written as a product of a function of omega s and omega I. So this is sort of the workhorse in a lot of quantum optics. There's been many techniques used to try to characterize this object, at least partially. They can be categorized broadly into two. So the first is these single photon spectrometers, which it's actually easier to do in the lab than it sounds because we have really great ways of measuring low-level light now. So one way to do it is to combine gratings with single photon cameras, or you can use these time-of-flight spectrometers, which I'll talk about a little bit later. So if you have one of these single photon spectrometers, then what you can do is just measure the spectrum of each photon and look for coincidences. And this joint measurement tells you about the absolute value squared of this joint spectral mode. Another very nice idea is called stimulated emission tomography. And the idea here is to, alongside the pump, you also couple a seed field into your downconversion crystal or whatever it is doing the nonlinear process. And this has the action of sort of stimulating the light generation. So you can also think of it as difference frequency generation. Okay, and so what you get in the green mode now is not spontaneously generated photons, but a relatively bright field in a coherent state. And the important thing is that the spectral mode of that green pulse is exactly the same as the spectral mode of the spontaneously generated photons. And by that, I mean that it's given by a cross-section of the joint spectral mode at the seed frequency. Okay, and so if you just scan your seed frequency and measure the spectrum of that green pulse, you can map out the entire joint spectral mode, again, in intensity. So both these measurements are lacking phase information. And phase is a lot harder to measure. You need some sort of interferometric technique. And it's a kind of a very well-studied problem in classical optics. And if you try to do it in a self-referencing manner, which might seem like something that you'd want to do, so you don't have an external reference pulse, you need some sort of optical nonlinearity. And obviously, this is very difficult to do with single photons. So there is one way around it, which is to use an external nonlinearity. So in this paper here, they took their single photon and split it into the two modes of this Mach-Zehnder. And in one of the modes, they sent the photon through an electro-optic modulator. This allowed them to apply a spectral shear to the photon, which is effectively the nonlinearity that they needed. And so they measured these interferograms that let them recover the phase of the photon. But this has the drawback that you still need this phase stability between the two arms of the path of the interferometer, and you need this external nonlinearity. So we were interested in, can we use a technique that relies on a reference beam? And we can go to the classical world where there's a lot of great techniques already invented. And so there's this idea of spectral interferometry. So now we're going to assume we have a reference pulse. And everything I'm talking about here is classical for now. Okay, so we know the spectral intensity of the pulse, and we know its spectral phase a priori. So if we have this resource, we can just combine it with our unknown pulse on a beam splitter, and then measure the spectrum of one of the outputs of the beam splitter. And what we'll see is an interferogram, which is given by this expression here. And you'll notice that the interference term here depends on both the spectral intensity and the spectral phase of the unknown and reference pulses. So we can isolate out the unknown spectral phase if we know the unknown, the reference phase. And this can be made a little easier by adding this little shear. So this is essentially just a delay between the reference and unknown pulses. You can do some Fourier filtering tricks, which makes extracting out the spectral phase quite a bit easier. So this is an example of amplitude interferometry. So it depends on the first order coherence of light. And the drawbacks in the classical domain is that it works for pure spectral modes. It's not clear how you would generalize this for mixtures. And you need phase stability between this reference and unknown pulse, which effectively means they're coming from the same laser. And that really limits the scope of this technique. And moreover, if you replace that unknown pulse with a single photon, you just won't see any interference. So, well, the good question you can ask is, what if you use the other output port of the beam splitter? So now we'll measure spectral intensity at both output ports. Again, everything here is classical. Again, now what we're going to measure is correlations between the intensities at the output of the beam splitter. And that's given by just the sum of the amplitudes and with the right phases. And the brackets here, the angular brackets, are just going to be some sort of average over many measurement trials. Now, because I don't want to necessarily assume that the reference and unknown pulse are from the same laser, I'm going to assume that the reference is phase randomized relative to the unknown pulse. And so we can model that by putting this e to the I phi, and phi is going to be fluctuating in time randomly. Okay, but for the experts here, phi should be fluctuating slower than the time resolution of your detector, okay, for this technique to work. So you do this classical ensemble, and because of the phase averaging term, a lot of the terms will disappear. Obviously, as you expect, if you're washing out phase, your interference should go away. But remarkably, what you find in the end is that actually there's some interference that survives. And so that's shown by this term here. And so this, like before, depends on both the amplitude and the spectral phase of the unknown and reference pulse. And this is without any phase stability. So what's going on here? This seems like black magic. It isn't. This is kind of a well understood thing that goes back to Hambry, Brown, and Twiss interferometry. And there's this very nice review paper that talks about some of the early experiments that Mandel did shortly after the laser was invented, where he was trying to look at interference between two independent lasers. And it uses this technique. Okay, so maybe it'll make more sense in a quantum description, oddly enough. So what's going on? If we imagine now that we have single photons instead of classical pulses, then suddenly this picture becomes very familiar. What we're doing is essentially Hung-Mandel interference, right? And so when we combine these photons, they should always exit that beam splitter from the same port. They arrive at the same time. And so we see a dip in this coincidences. And the visibility of that dip depends on the mode overlap of the photons And if you don't have perfect photons, it'll also depend on the photon statistics, so the amount of intensity fluctuations you have. Okay, and so if you have good single photons, you can get up to 100% visibility. If you use phase random coherent states, which is the example in the previous slide, you can get up to 50% visibility. And if you have a single photon in a coherent state, then you're bounded by V alpha, which was studied in this paper here, and this is what the visibility looks like. Okay, so I can make a connection here to Rob Speckin's talk. We usually think of Hongo-Mandel interference as this prototypical quantum interference effect, but it does have a classical analog. And as he mentioned, you kind of have to quantitatively look at how does this interference effect depend, in this case, on the intensity fluctuations, to really say something about the non-classicality of the effect. Right, so this is essentially what we're doing, is spectrally resolved Hongo-Mandel. Okay, and so we're going to combine our unknown photon labeled by psi here with the reference on the beam splitter, and then look for spectral intensity correlations at our single photon detectors. And as I mentioned before, if you know alpha, you can just divide that out and work out what psi is. Now, why is this fine? Well, because alpha can just be a coherent state. So this means that you can start with a strong laser, send that pulse through commercial devices that let you do self-referencing characterizations through techniques like Spider and Frog, and then just attenuate it down to the single photon level. You've got a good reference that you can use for your measurement. Again, this works for any quantum state of light, including mixtures of modes. So that's for a single photon. We can extend this to photon pairs, and so the idea is shown here. So we are generating these pairs of photons. We'll send the idler mode, so the orange photon, directly to a spectrally resolving detector. Suppose we measure omega h. This heralds a photon in the other mode, which is given by a cross-section of the joint spectral amplitude at omega h. And then we just determine that cross-section using the technique I just mentioned, and we repeat this for all the different herald outcomes. Again, this way we're going to measure all the different slices of the joint spectral mode. So here's the experiment that we built. We started with a pulsed telecom laser. We split the pulses into two. In the bottom path, we prepared the reference pulse. This is just the attenuated coherent state. And that was coupled into a single mode fiber. In the top path, we frequency double the pulses and then pump this periodically pulled potassium titanyl phosphate waveguide, which is the down conversion source that we chose. And the reason that we chose the source is because it's quite bright. And in particular, it has this property that the down converted photons are in principle spectrally uncorrelated. Okay? These are some group velocity dispersion engineering. And so there's been a lot of work exploiting this property from these waveguides, and we wanted to do phase sensitive measurements of the joint spectral amplitude to really see confirm that this is exactly what's coming out of the waveguide. Okay, so the photon pairs are separated at the polarizing beam splitter. The idler, which is in the top path, goes directly to the spectrally resolving detector, and the signal gets coupled into the fiber and combined with the reference on the beam splitter. We measure both outputs with the single photon detectors. So the spectrally resolved detection here is just done by this time of flight spectrometer. So we send the light through a long optical fiber. Now, glass is dispersive, so essentially what happens is that the different frequency components of the pulses travel at different velocities. It chirps the light. Because the fiber is very long, you get a pretty good mapping of the time, or the different frequencies of the light to their arrival time at the detector. Okay, so we have a time tagger, and we look at when the photon arrived at our detector, and we can map that onto a frequency. So here are the results. This is for a particular herald outcome. We're combining the single photon with the reference on a beam splitter, and we've introduced a time delay between the two pulses for reasons which will be clear in a second. So this time delay introduces this regular fringe pattern in the interferogram that you see. So the inverse of that period is given exactly by the time delay. And so from this quantity, we can take its Fourier transform. And what we see are three blobs. The center blob is just all the non-interfering stuff, which doesn't depend on the spectral phase that we don't care about. The the side lobes contain the good stuff, so that has the spectral phase. And so what we can do is apply a filter in Fourier space, a window function, isolate that term, and then just divide out the alpha and this shear term, which we know because we decided what the shear was. Okay, and then what we're left with is this quantity here, which we can diagonalize if we assume we have a pure state. And what we get out is the amplitude and the phase of our single photon. So we repeat this for all the different Herald frequencies, and then we stack up the modes that we measure. And we get a picture like this, which tells us about the joint spectral mode of the photon pairs. And in this particular case, what we find is that the joint spectral amplitude, which is on the right here, is this kind of oval shape, and it confirms what we expected. It's uncorrelated in the two frequencies. And this is also true in phase, where we just have a flat phase, nothing interesting. Okay, and so we can quantify the degree of correlation by doing something called a singular value decomposition, which gives us this Schmidt number of 1. Okay, so for the experts in the room, confirm this agrees with an autocorrelation function of the downconverted modes. So then we wanted to do this with a more non-trivial phase. We coupled the pump pulse into a fiber. It gives it a chirp. And chirping the pump pulse is the easiest way to get some interesting phase correlations in your photon pairs. And what ends up happening is that you get this correlated phase between the signal and either frequencies. And this is indeed what we see in the measurement. Okay, so we see these correlations. And the amplitude is largely the same. Okay, and so now if you do this Schmidt decomposition, you find that your Schmidt number went up by a factor of 1.5. So the purity also was reduced by about 50% because of these phase correlations. So that's good. It requires you to measure threefold coincidences, which can be problematic if your source is not very bright. So what we wanted to do is exploit the fact that there's nothing inherently quantum mechanical about this interference effect. We can use it with classical light. So we combine this idea with stimulated emission tomography. And so we can couple a seed into the crystal, produce a classical pulse, which is given by a cross-section of the joint spectral amplitude, and now try to measure the mode of that thing using our technique. Okay, and so we confirmed that we indeed get classical light by doing the seeding process, by doing a G2 measurement, and combine that with the reference, and we also see interference fringes. Okay, the visibility is reduced compared to the previous slide, and that's because our signal is now this coherent state. It has more intensity fluctuations than the single photon, which reduces the fringe visibility. And so this is obviously much faster because we're dealing with classical light now. And the cool thing is that the seed laser and the pump do not need to be phase locked with one another. Okay, so we're really interfering light which is uncorrelated in phase. Right, so okay, that concludes the spectral mode measurement. And now I'd like to talk about some ongoing experimental work at the NRC where we're extending this idea to the spatial domain. So usually when you're doing imaging, you're typically only concerned with the intensity information that the light beam contains. But of course, when light passes through an object, it picks up a phase. And in general, that phase can be useful. It can contain information. So this problem of doing both amplitude and phase determination is known as wavefront sensing, or sometimes holography. And it's kind of what underlies this idea behind phase contrast microscopy. And you can see that the phase contrast microscope, which converts the phase information to interference information, like any interference effect, basically it's much more sensitive to the edges of the sample, right, where you'd pick up a kind of phase jump. So that can be useful. So essentially, it's the exact same thing as I showed in the spectral domain, but now in space. And the nice thing is that your signal can be coming from quite far, and because this doesn't rely on phase stability between the signal and the reference, you don't have to worry about the fact that it's coming from far, essentially. So you measure now the joint probability to get a particular x1 and x2 at the output of the beam splitter, and like before, you measure this interference term. This interference term, whose visibility will depend on the photon statistics of the signal and reference. Okay, so you can kind of think of this like Hanbury, Brown, and Twist, but we have this external reference beam here. So here was the setup that we built to test this idea. So coming out of these single mode fibers, on the left, we have the coherent state. And so it comes out with a Gaussian spatial mode. On the right, we are either going to use a heralded single photon or a coherent state. So this will be the signal. Now, to encode some interesting spatial pattern, we send that light through an SLM, which allows us to encode amplitude mask as well as a phase mask. And so these are the two quantities that we're going to want to determine, T and phi. Oh yeah, I should also mention that the coherent state gets sent onto this piezo mirror, which is shaking, and this is just to mimic the phase instability. So we want to mimic the fact that the coherent state comes from far away, basically. It's not phase stable with the signal. Okay, so we interfere these two on the beam splitter and then image the beam splitter output on the camera. So this is kind of what allowed us to do this experiment, is this amazing camera called the Timepix. So it has about 256 by 200. It has 256 by 256 pixels. And the amazing thing is that each pixel has a time tagger behind it, and it tells you when that pixel fired with like a few nanoseconds time resolution. And so this is exactly what we need to do this correlation measurement. We can just look at when 2 pixels fires within some correlation window. All right. The drawback is that the efficiency is not so great. Okay, so here's an example of a sort of measurement we can make. So this is just a simple 1D quadratic phase. So we're applying this phase mask on the SLM. And so we see 2 beams, the 2 outputs of the beam splitter on the camera. And because we're shaking the phase at the piezo, we don't see any sign of interference at the camera. If we just look at intensity, right? This is what you'd expect. The first order coherence interference effect gets washed out. But now if you look at coincidences, suddenly you see this fringe pattern. And so here I'm looking at just the x coordinates because everything is symmetric in y, so I can just sum over that and just look at what's the fringe pattern along the x dimension. We did this for single photons as well as with coherent states. Okay, so in principle, you'd hope that the single photon interference pattern should have a little bit higher visibility than the coherent state because of the reduced intensity fluctuations, but due to noise, we're kind of on the limit. They're roughly the same. Okay, and then we can do the same trick as before. I'm not sure what's going on with those label axes, but that's fine. So we can apply the spatial shear, which we just tilt one of the beams going into the beam splitter. And now we introduce this regular fringe period in the pattern. We can do the Fourier filtering trick, which I mentioned before, and get out the absolute value and phase of the signal. And in this case, we do recover the quadratic spatial phase that we encoded on the photon. Okay, so we can also do this for 2D phase masks, which is the image I showed on the first slide. So this is a sort of whimsical picture that I chose for this conference, the maple leaf. So now we're measuring this 4-dimensional joint probability distribution, which is a little bit difficult to wrap your head around. But one way that you can extract out some images that make sense and show you some phase information is to look at particular regions on the left beam. So you select a pixel on the left beam, which will correspond to like the different regions on this phase pattern. So in particular, different phase values. And so what we see on the right beam, depending on the region that we select on the left, is a different intensity image, right? And so what's going on here is that the selection that we make on the left is serving as a phase reference for what we see on the right. Okay, and so in this way you can measure the phase of work out what the phase of this smiley face is. Right. Okay. So with that, I'd like to summarize. So I hope I explained this concept of intensity interferometry, which we can use for modal characterization of light, and the two key points which makes it, I think, potentially useful for experimentalists is that you don't need any phase stability between your reference and your signal beams, and it also doesn't require any nonlinearities. So when you're doing the temporal spectral characterization, that's quite useful. Again, we used it for measuring the joint spectral mode of photon pairs, and we're doing ongoing work for extending this to the spatial domain. I think in the future it'd be interesting to try to characterize polarization as well, and in particular looking at these vector beams that have these correlations between polarization and spatial degrees of freedom. And I'm also curious about what happens when you go beyond just second order correlations. What if you look at higher order correlations? Can that be useful for anything? Okay, yeah, so with that, I'd like to thank you for your attention.